Not yet.
Okay. So yeah, so we will see that. We'll let us. I'll tell you how people evolved to transformers and talk about transformers as well, and then we can close. Okay.
We have distillation also we plan to
Knowledge
discuss.
distillation is pending.
Distillation is pending. No, okay. So let's start with distillation and then move to sequenced models. Then. Okay. Thanks for reminding. Okay. Okay. So this was an idea that was proposed by Hinton and his group in in early late 2000s, I think. It's the objective here. It's not the primary objective, but still the context in which distillation is used today. The objective is to reduce the size of
Sir, are
very
you
large.
sharing something?
Don't you see my screen?
Not yet, sir.
Oh, sorry. It is saying that it is showing the screen. Okay, let me do it again.
At least I am not able to see, sir.
No, no, it is not shared.
No, still not seen?
No, sir.
How come? Let me rejoin from here. Let me know when you see the screen.
We can
You
see
do?
now, sir.
No?
Now we can.
Okay.
Yeah.
Okay. So the objective here is to reduce the size of very large neural networks without compromising the performance. This is the objective. The idea is pretty simple. When it was proposed, it was proposed without further understanding of what was actually happening. I'll tell you what it is. So in knowledge distillation, what happens is you have a very large neural network that is to be compressed. So large neural network to be compressed. It is usually called the teacher network. Okay. Then you have another neural network. With the desirable size. That is called the student network.
Sir, I have a question.
Uh, let me complete this and then tell me what is it.
Sir, this is related to like a bit related to the assignment. So like in the animal data set, we have around 5,500 images divided among 90 classes, right? And even when we were going for the classification tasks, we saw that the training accuracy was very high, but the testing accuracy is always very low.
Hmm.
So what my perception was, since the data, this the data size is very small, like we have good number of classes but not sufficient images per classes. That is the reason that the model is able to learn the features like, remember the features, and not able to classify properly on a newer set of images. Is that the correct interpretation?
Yeah, why? What is the relevance of that question to what we are doing now? I think it would have been asked at the end of the class, right? Anyway, so
Yes,
now that you have asked,
yeah. So
yeah.
the
So we
reason
were
I am
looking,
asking,
at distillation. I think after this, after I had finished this part, you could have asked anyway. Yeah, that can be one of the reasons. So what happens is when your data has multiple short modes. So you can think of each of the classes as one data mode. And typically, when the data set has too many modes, okay, with very less samples amongst each of the mode, then getting a discriminator or a classifier that would put decision boundaries across those classes would be difficult. Yeah, so in that way, your interpretation is correct.
okay, okay, sir.
Shall we continue with what we were doing? So if you have any questions on assignments, etc., please note that down and ask at the at the end of the class, okay? Huh? So that it does not break the flow of what is being done. Of course, you can ask questions regarding what is being taught. Okay. Anyway, where was I? Yeah. So distillation, two neural networks, one large neural network that needs to be compressed. That is typically called the teacher network, and there is another neural network with the desirable size, which is called the student network. Okay. Now, to teacher network is trained with a supervised objective. Whatever, suppose you are solving a classification problem, it is solved with first objective with cross entropy loss and whatever the supervision might be. Okay, supervised objective independently of the student. What happens is a network here. Whatever the task might be. Okay, let us call this the teacher network. So some data, some task, and it is trained with minimizing. Let's call the parameters theta, just usual minimizing the expected loss function. Okay, which is between okay, let's call this f theta, maybe f theta of x comma y. Yeah, so this is the usual empirical risk minimization, okay, or supervised training. Now there is a smaller neural network which is called the student network. The same pairs of x and y. is phi. Okay. Now this has two objectives for training. One is a KL objective between let's call this CT and this as CS. KL objective between the distribution of ZT and the distribution of CS plus a supervised loss. So phi plus supervised loss between X and Y. Okay, so what is happening here is that when the student network is being trained, okay, now the KL divergence between the distributions of some features in some layers, typically the pre-softmax layer of the student and the teacher network is minimized. Okay, and there is a supervised loss that is minimizing the uh, loss between the real true predictions and the predictions of the neural network. Okay, so now what is this doing is this trying to match the features, learn or match the features of teacher, okay, to set of students. So that is what it is doing, right? By ensuring that the KL divergence between the distributions of representations between the argue about it. So by ensuring that the KL divergence between the features of the teacher and the students are matching, I mean the idea is to ensure that the uh, uh, features that the teacher has learned is imbibed by the student. If it does that, then whatever the performance that the teacher is supposed to give with a larger network can be achieved or can be expected to be achieved using the student network. Okay, so procedure wise, this is what is done. So in practice, the KL divergence term, no, between the teacher features and student features is approximated via so mean squared error loss. So squared error loss average, it is actually mean squared error loss between ZD and ZS. Yeah, this is also not a bad approximation, right? When we assume these two distributions, PT and PZ, actually what this actually means that to have PT coming from a Gaussian, okay, and PS is also coming from a Gaussian. If you make this assumption, then we know that the Scale divergence is equivalent to minimizing the mean squared error between the features taken when averaged over all possible mm, samples. Okay. Okay. So this is how the finally what is done is instead of using the teacher network is discarded, meaning it is I mean it is the goal is to not use the teacher network but to use the student network for further processing. So that is the idea. Okay, so I will tell you. So there is this was what was being done in distillation. Um, Now, a very recent paper came that gave a very nice statistical perspective of why should this work. Okay, what is actually happening under the hood. I'll talk about that. Before that, if there are any questions on the procedure of what distillation is, do ask. And by the way, in your assignment, what I've asked is, I've asked you to use a larger teacher network and distill it down to a smaller student and compare it with just training the student network separately. I mean, meaning a network that is of the size of the student network separately and then compare the performance. Okay. Okay. Questions now. Yeah, Vivek.
So, two small questions. So, should the sizes of the features of the Z and the I mean both the ZT and ZS, should they both be the same
By sizes, you mean the dimensionality?
dimensions? Yes.
Yeah, they have to be same. No, otherwise, how would you define KL divergence?
KL term. Okay, so the second question is how important is the KL divergence term in this? So if we skip that and if we simply use a completely different network, so is that still called a distillation?
What do you mean by that? See, if you do not use any features from the teacher, okay, while training the student network, then there's no distillation, right? It is simply an independent training,
Right. Okay.
isn't it?
Yeah.
I mean,
Yeah.
see, it is called distillation only because you have a teacher network and you are using those features to uh, uh, you're actually imposing those features on the features of the student. That's all, right?
Right. Yes, sir.
It's like whatever teacher network has learned, the transformation that the teacher network has learned, you're trying to ensure that the features of the student network matches those features at a distributional level.
Yeah, but if the student network is struggling too hard to simply match with the teacher network more than increasing the accuracy of the classification task,
Mm,
then
mm.
should we reduce the weightage on the KL divergence
Yeah,
term?
of course, of course, of course. I mean, that's always there, right? I mean, when you have two loss terms, you always weight them accordingly.
Okay. Yes, sir. That's all. Thank you.
Yeah. Okay. Okay. Yeah, Sarvesh.
Sir, if Z are just the softmax terms, so why to include this expected loss in student network? Because anyways, they will be same, right?
Uh,
If they are same, then
yeah. Good question. See what happens. This is a practical thing. What happens is when you do not have the supervised loss, because I mean teacher network may itself have not learned to solve the task properly, right? The performance of the student network will not be great if you don't include that.
because just to be sure that it is learning the main.
Correct.
Okay.
Correct. Whatever is needed, no, the main learning should happen. That is why the supervised loss is also included.
All right. Thank you.
Sanjit?
Sir, if the teacher network is like as we are asking, it is very large, and let's say uh, the data size is not sufficient enough for the learning to happen correctly, and at the same time, then we are trying to use that loss for training the student network. So, how can we expect the student network to be learned properly?
Yeah, you're saying if the teacher network is bad, what happens to distillation?
No, no, like I asked a previous question, right? If the data set is not sufficiently large. So we cannot expect the teacher network itself to learn the classification properly, and then we are trying to train the student network.
That is what, no, what happens if the teacher network itself is not good?
Hmm, hmm.
That is what you're asking. Yeah.
Yes, sir.
Yeah. So, yeah. So what happens is if there is uh, some level of uncertainty in the teacher network is okay, right? As we will see in the theory. But if teacher network is not even doing uh, supervised learning, right? Then obviously the student network will perform badly. Yeah. So we'll have to ensure that the teacher network has to have some level of good accuracy for this to work.
Okay.
Okay. Anything else? Okay. Shall we continue?
Yeah, just one small query. What is the benefit? Is it going to use less resources?
So training, definitely not. But inference, of course, right? Because the student network is by design smaller in terms of sizes. Uh, it is going to use less resources during inference. Because finally, what you end up storing is the student network, not the teacher network.
Okay.
Hmm? Okay.
Sir, one more
Good.
question. The training has to happen simultaneously, or uh, first we have to train the teacher network and then the student network?
Hmm. So that's a design choice. Typically, what is done is uh, teacher network is trained up to some level, okay, where you have decent accuracy, and then both of them are trained simultaneously. But you can completely train the teacher network once and then freeze it and then do a distillation. That is also possible. That's a design choice.
Okay.
Okay. Okay. So yeah. So this is what is done procedurally. Now, as I said, no, there is a very nice uh, interpretation so as to why this works. Let's try to look at that. Statistical perspective on knowledge distillation. Okay. Uh, okay. So what happens is in typical supervised learning, the labels are deterministic. In the sense that every data point, so okay, let us design the problem that way. Suppose the class labels, right? They belong to uh, one out of k categories. Okay, in a k class classification problem, then typically for each x, okay, y is only one of the k plus 1 labels, right? This is what happens. However, there is always uncertainty in labeling. Certainty in labeling. So, which implies that for each x, there exists a distribution over y. P of y given x. So what I'm trying to say is, let's say that there is you have an image that you want to label. Okay. Now, okay, so I'll take an example that is sort of ambiguous. Okay, I should write it not like this. Okay, which digit do you think it is? I mean, let's say that I'm annotating mnest.
I.
Yeah, if I do this now, so people write it this way, no? So this means that this has some likelihood of being in 3 and some likelihood of being in 5. Right? So now there exists, so what is this? Along y-axis, what I've written is, this is P of y given x. Okay. Now, what is done in typical supervised learning is, okay, in supervised learning, P of y given x is approximated with a delta function. Isn't it? So the uncertainty that is associated with the labeling is completely ignored when I mean in typical supervised learning, right? Now, what this nice paper does is the following. They consider, okay. So any questions so far? I mean, what I'm trying to say is there is an uncertainty that exists with the labeling inherently, because every data point can probabilistically belonging to one of k possible classes, but labeling is always done in such a way that uh, the uncertainty that is there in the labeling is ignored, and labels are given in a deterministic way. Is this clear?
Yes, sir. Yeah.
Okay. Now, what is the consequence of it is the following. Define two types of risks or losses. One is the typical supervised loss. Supervised loss with deterministic labeling. Call it R. Okay. And there is, okay, let's call it R cap. And there is something called base distilled loss. Okay. Base distilled loss, call it RB cap. Okay. Now, this is what can actually be shown as that this is, we know what R cap is, right? This is simply the expectation of the loss. F is the classifier that we are looking at. This is f theta of x comma y. This is what it is. This is with respect to pxy. and this can be shown as scale divergence between the distribution of uh, f theta of x, theta of y given x, let's say. The classifier imposes a distribution on labels, right? That is what it does. And the true label distribution, that is what you can show. Okay. I mean, if you use a cross entropy kind of loss, then the scale divergence is equivalent to that cross entropy. I mean, that is easy to show. Okay. The interesting result that which is shown is, now suppose R star represents the generalization risk. Or it's also called the true risk, which is nothing but the error, average error on unseen data. Average error on unseen data. Okay. What can be shown is that R star will be lower for RB cap, okay, compared to R cap. So this is actually the main result which is there in that paper, which uses Jensen's inequality, okay, to bound the variance of these two risks. Yeah, but this is the crux of the result that would say that the generalization error that we get, the generalization error that is achieved using base distilled risk is lesser compared to that of the risk that is obtained using the Dirac delta approximation. Okay, which means, so what does this imply? Summary is, it is better to use base distilled risk or the distribution, the actual distribution over the labels given data, okay, instead of delta approximated labels. So this is the idea. Okay. So now this paper says that now see if you incorporate the, I mean, that is why this thing P of y given x is also called dark knowledge. That is the term that is used in the distillation literature. Okay. If you incorporate the dark knowledge that is there in the labeling, or uncertainty that is there in the labeling, you achieve a better generalization performance is the idea. Now, this is not directly related to connected to distillation yet. Okay. Now the question is, given a labeling, a deterministic labeling scheme, there is no access to P of y given x, isn't it? I mean, we are only given deterministic labels. How do we know what is the distribution of the labels conditioned on data? We don't know that. Okay. Therefore, the idea is, the idea is to approximate P of y given x, okay, as, or rather using a neural network. So this neural network is the teacher neural network, right? So now what happens is, in fact, this theory, right, it does not talk about the size reduction at all. So it suggests what is called as self-distillation. I'll talk about it. So there is this network f theta, that you get x and y. It is trained in a supervised way with deterministic label. Okay, supervised using deterministic labels. However, the pre-softmax uh, activations that you get, the logics that you get, these can be interpreted as an approximation to P of y given x. So this is an approximation to P of y given x. So then what you do is you take another network. We don't talk about sizes here, right? I mean, it can be the same size or different size. If it's of the same size, then it is typically called the self-distillation. Okay, take that and use RB star here to train this. So now RB is the base distilled risk, is simply the scale divergence between the true, or rather the model's estimate of y given x, okay, and the true y given x. So now we don't have access to true y given x, so we use the features f theta's logits as an approximation to this. Now, when somebody asks the question, right, we can, why do we have a supervised loss? So if we have a perfect estimation of P of y given x, then we do not need supervised loss. Now, since we are approximating the true uncertainty, label uncertainty using another neural network that is trained using deterministic labels, so it can only do so much, right? So that is why you also have a supervised loss here, okay, to ensure that the network, the distilled network, also does well on the supervised training. As I said, no, in this treatment, there is no reference to making this SP a smaller network. No, that becomes a byproduct, right? Or a happy consequence of this. That okay, there is no restriction on how big or large this SP network should be, because as long as you are matching the true label uncertainty, you should get better risk irrespective of the network size, and that is why people tried, okay, let's try to make this SP a smaller network and then uh, try to ensure. So there is the scale here, and try to use this technique for network compression. In fact, as it stands, you can do what is called as self-distillation, which is that you train a neural network using supervised fashion, and then take that same neural network and use the logics of the previous one and retrain it by minimizing the KL between the logics and a supervised loss. I mean, if you have gotten P of y given x to a fair extent from the teacher network, then doing self-distillation should improve the generalization according to this theory. Okay. Okay, that's about it. Questions? Yeah, Vivek?
So you told about the base distilled loss,
Yeah.
but instead of using that, so if we just use the entropy of the pre-decision layer output, I mean, if we try to um, minimize the entropy, will that lead to any benefit?
That's same as this, isn't it?
That's what it should be, less indecisive.
Yeah.
That way the entropy will reduce. Yeah,
Yeah.
yeah. So okay.
It's very in fact, it's not the absolute entropy. It becomes I mean, what we are suggesting is to minimize the cross entropy here.
Cross entropy. Okay, between the teacher and the student.
Correct. Correct.
Okay.
I mean, it's actually not the teacher. It should be the true distribution, the true posterior of labels given data. That is what it should be. Now, because we don't have access to that given hard labels, we will try another neural network and use its logits as an approximate for that. That is the idea.
Oh, okay.
Yeah.
Okay, sir.
Okay. Yeah. Any other question? Harish?
Sir, if the student network, the size of the student network is not so small, it's almost same to the teacher network, then what is the benefit of doing this? Because we can directly do the
Yeah, I told you, no,
supervised.
it is improved generalization. It will do much better on test data, unseen data. Because now you are not training this neural network just using hard labels, but you are training it using, I mean, you are incorporating the uncertainty also that is there in the labeling.
I see. Got it. Thank you.
Sanjit?
Sir, for the supervised loss, we will be taking up the true labels Y and the approximated labels from the S5 network, right?
Of course, yeah. You're saying while you are doing supervised training for the student network, you're saying, yeah?
No, no, no. Uh, I'm trying to understand, like, uh, with what are we comparing? Are we comparing it from the uh, labels generated from F theta network or from the SV network?
True labels. Here, the supervised losses with these true labels. The output of the SV network and the true labels. That's what the loss is between.
Okay. And this F theta network, so this can be any network, right? It need not be trained. Just that we need a representation for
Well,
P.
if it's not trained, then how do you expect it to give the actual P of Y given X?
Okay.
Should be trained.
Okay.
Should be trained in a
Okay.
supervised way. Yeah. Okay, so that's about it. And yeah, this is how you implement it in your assignment, right? I have not asked you to do self-distillation. I've asked you to reduce the network size and do a distillation on reduced network size itself. So yeah, please do that. And also read this paper, okay? This is called A Statistical Perspective on Knowledge Distillation. I think I'll tell you the authors also. Just a second. Statistical perspective on knowledge distillation. Better to share the link, no? Let me do it. Do you see my screen? Hello?
Yes, sir.
I see my screen, right? So this is that paper. So here, what they do is the following, right? Yeah. So they call this as what? Yeah, this PT of X is what they called as the teacher class probability estimates or the true label posterior. Okay, so where PT of y given x estimates how likely x is to be classified as y. Now these are used by a student model which replaces empirical risk, which is the standard empirical risk, with the distilled risk. This is what they call R tilde is what they call as the distilled risk. Okay, then the question is why does distillation help? Okay, so they compute this thing called base distilled risk, and this is the main result which I just said, that if you take any bounded loss, then the generalization error that we get with the base distilled risk is much lesser compared to that of non-distilled risk. That is the result. Okay, so I suggest that you read this paper. It's a nice paper, and the proof that they use to show that is also not very difficult. It is simply using the definitions of variance and using the Jensen's inequality. That's all it is. Have a look, please. Okay. It's about distillation. Do you need a 5 minutes break, 10 minutes break before we go to sequence modeling? Hello, am I audible?
Yes, sir.
Shall we get back after a break?
Yes.
Yeah, so this is okay. So let's come back at 11 a.m. Maybe just take some 15 minutes break.
Yeah, sure.
Okay, yeah. See you in a while.
Thanks. Bye.
Hello? Shall we continue?
Yes, sir.
Let me just share my screen. Yeah, Vivek, you have a question?
Yes, sir. So I was just seeing the paper. So what is temperature scaling?
Oh, yeah. So that is like, I think it was you or somebody else who talked about the weighting of those two losses, no?
Okay. Yes.
The supervised and the KL losses.
Okay.
That is what is referred to as temperature scaling. How much weight do you
Okay.
have to give for each of them?
Okay. Okay. Uh, okay, so okay. So what is a well-calibrated model? So what can we do to what? How should the temperature be scaled?
That's a hyperparameter. That's all.
Okay. So should we learn that hyperparameter
Well,
or should?
yeah. See, just like with any other loss functions, right? I mean, where you have two or more components and you need to decide the weight. Either you can do it using hyperparameter tuning, or you can learn it. In fact, I have a paper sometime back, 1 year, 2 years back, where we cast it as a meta learning problem and learn both the weights, loss weights, and the losses together. All that is again level up, but yeah. So typically it is trained as a hyperparameter. Either you learn it or keep it. I mean, fix it based on validation data.
Okay. Okay.
Yeah.
So
Okay.
can we have a link to that paper if you don't mind? I mean
I
later on.
shared it, no? I actually
Okay.
shared it
Okay,
in
it's the
chat.
same paper. Okay.
So you mean my paper you're saying,
Yeah,
huh?
yeah.
Hold on. ALMKD. The paper. Not getting the link.
Maybe you can share the name and the title.
Your title is there, but I myself should find my paper. No, where is the? It's published in AAA, but where is the link for it? A second. Uh, Surprising that I can't spot the link. PDF is here. Finally, I got it. Yeah, I just put it in the chat window. So what we do is that wherever you have these kinds of settings, right, where you have like two losses and you need to,
Okay.
in fact, one of the applications is knowledge distillation. If you look at section 4 of the paper,
Okay.
we actually learn that temperature.
Okay. Knowledge distillation. Yeah. So two applications in this. Okay.
If you look at equation 9, 10 and all that, we actually learn that and show that like there exists an optimal value. We do it using uh, this thing, meta learning. Yeah, that is what the paper is about. But generally that is not done. It is taken as a hyperparameter and used to validate, fixed based on validation data. Okay.
Okay. Just through some sample values and what
Yeah.
is giving the good
Validation
result.
data.
Okay,
Yeah.
okay, validation data. Okay, okay, so thank you.
Okay, let's move on. So the final piece that we will talk about is the sequence modeling. So, data in this case will every data point, okay, is a sequence. Okay, data point is a sequence. So what do you mean by a sequence? Let's say that X is one data point. So one data point itself will have a superscript perhaps, huh? To X T, okay, where every Xj is in some d-dimensional space. Okay, this is what is called as a sequence, where every data point has a is a series of d-dimensional vectors, t of them. Okay, so examples of this, you know that this is you have a sentence, right? Is a sequence of linguistic tokens. These tokens can be characters or words or something, right? So the other example is the speech signal. This is a sequence of frequency domain vectors, typically called the MFCC and so on. Okay, so this is one thing, and you have uh, some industrial time series, and you can also look at video as sequence of images or frames. Okay, so this is a sequence. I mean, this is what is called as a sequence data. Now, sequence modeling is set of all those methods where the objective in sequence modeling, the objective is to solve the objective is to solve either discriminative or generative or generative problems on sequences. On sequences. Okay, so now there you have examples of these problems. So examples can be, of course, we have machine translation, where you have a sequence in, right, a sequence in one language, sequence in English, and what comes out is a sequence in Hindi, let's say. Right, so this is one example. The other example can be uh, text summarization, right? You have video classification, spam detection, and so on, right? I mean, you can think of any number of problems that we have that you can encounter within sequences. Okay, so now how do you deal with this kind of sequential data? Is a question that people have been asking for a long time now. Uh, Now I'll just give you broad history of how things were happening, and then we'll move on to what the current state of the art is. History of sequence models. So very early days, right? People were using uh, models such as auto-regressive models or AR models, where the idea was the following. So you have to model XT, right? So XT was modeled as simply a linear combination of one to, or rather, let's say t minus k to t. Okay, so this is an auto-regressive model where you you model, or rather you express the tth sample. Okay, so we used a superscript for t, no? The tth vector that we have is given as a linear combination of, see, I don't want to confuse you by using superscript and subscript. Okay, let us use subscript only. Don't confuse it with like 1, 2, 3 up to t data points. Okay, in one data point itself, you have uh, t length sequence. It is okay. So that is what the convention is. Xt is equal to okay. So now what we are doing is every tth token in the data is a linear combination of a k length window before it. Okay, this is an auto-regressive model. I mean, you can imagine why the name, right? It is regressing on self. Okay, that is why it is auto-regressing. So it is not using anything else. It is only saying that okay, I will express, or rather the tth token is expressed as a linear combination of previous t minus k tokens. It is also called linear prediction model, linear predictive coding, or LPC. In fact, even today, this is used in telecommunication, okay, to compress speech and all that. So now the question here is, how do you find these coefficients A? And it is found out in a statistical way, where you have a lot of data and try to reconstruct the data back using the k previous samples and find out these coefficients and use them. In fact, what is done in speech compression is that you need to transmit speech data from one point to the other, let's say, right? The raw data is not at all transmitted. What is transmitted are these coefficients, AJ, so that you can, I mean, that is a compressed version of it, okay? And then you use that and reconstruct the data back at the decoder. That is, in fact, as I said, no, as we are speaking, a lot of VoIP protocols and all this, even today uses some variant of this linear predictive coding. Okay. But the thing is, these kinds of models work with speech kind of data where there is a lot of predictability, but they don't uh, generalize for tasks like machine translation and so on. Okay. People then move to statistical models, such as one example was one famous example was what is called as a hidden Markovian model, or HMM. HMM was the go-to model, right? To model sequences, go-to choice for modeling sequences for a long time. What is the model here is that you assume that there's a Markov chain, okay, amongst what are called as states. I'll tell you what states are. Another transition from here to here. Okay. Okay. So and every state emits symbols. And these symbols are xj's, x1, x2, up to x. I mean, it's simply xj. Okay. So now these are states z. So it's actually HMM, right? Is a latent variable model. It's a latent variable model. Where the latent variable is discrete Markovian. Okay, and the model is the following, right? There is a Markovian transition between the latent variable states, and at every transition, right? After every transition, the model emits an observable symbol xt. Okay, this is continuous and model using neural net GMMs. This is the HMM, the famous HMM GMM model, where see basically what is happening is the following, right? I mean, imagine the speech signal example. So the motivation behind this is this assumption that when somebody is speaking, okay, what is actually happening is that before you speak, you think of what is the phoneme that you have to emit given the semantic meaning that you want to convey, okay? Depending upon what uh, phoneme that you need to emit, okay, or phoneme you need to convey, you create some constrictions in your vocal fold, and what is uh, produced is a pressure difference. Okay, when we speak, what happens is, there is a certain pressure difference that occurs in the environment, which is what is recorded using a microphone, a condenser microphone. So this is the observable speech signal. These are the observations, which happens to be the speech signal itself, which we measure. Okay, so what is Markovian are the unobservable abstract phonemes. Okay, so now there is a Markovian transition between them, because given that you need to convey something, and given that you have already said a particular type of phoneme, you can only choose from I mean, there is a probability from which you can choose what phoneme to be uttered next, right? Right. So that is why there is a Markovian assumption between the hidden states, and what is observed are the measured quantity. Okay. So this is a model, and the distribution. So now basically what happens is there will be a distribution amongst the states. Okay, which is Markovian, and there will be a distribution over the observations given a particular state. This is modeled as a Gaussian mixture model. Okay, this was actually the standard. This used to be the standard modeling choice for any sequences, where you say that okay, so you can extend this for, let's say, handwriting recognition, right? Where the observations are modeled as the pen strokes or the coordinates of the pen strokes, and the latent variable or the z models what is the um, uh, letter, or rather the symbol that is to be conveyed. Okay, And if you want to model speech, as I said, there are phonemes, and every phoneme emits a symbol, which is a speech signal, and so on. Okay, so now what are to be learned? So this is parameterized by some theta. This is parameterized by from phi. Theta and phi are learned using the EM algorithm. So we have seen the EM algorithm, right, in the very beginning classes. So EM algorithm is used to learn this. Okay, so this is how initially the sequence models were being learned. So if anybody wants to learn more about HMMs, right, there is one very nice tutorial by Lawrence Rabiner. Have a look at it, where he formulates the problem and write down the log likelihood for an HMM and works out the EM. So basically, it is working out the EM. Okay, HMM tutorial. Okay. Any questions so far on this?
So, but in this Marco model, are we actually passing is it dependent on the past? I mean,
It is, no? It is.
yeah,
Because
okay,
it is Markovian. Yeah.
right.
Uh, Sir, just to know, I mean, you said when we say a sentence, right? We say one word and the word is basically we can predict whatever is the next word, kind of, right? I mean,
Not
that's
predict.
what.
There is a probability over what the next word is going to be. That is reasonable. Because
Yes,
if you are because in a given language, given that you have uttered one word, there is a certain probability of what the next word is going to be.
but for Markov, it just depends on the previous word alone,
I
right?
mean,
But
it depends on what order of the Markovian assumption that you are making. You can make it a first order Markov, second order Markov, third order Markov, anything. It's called an
oh,
n-gram model, right?
okay.
You can make it a unigram, bigram, trigram, anything, right? So it is not one word always. In diffusion models, we assumed it to be a first order Markov process, but it need not be first order. Typically, it is taken to be a third or fourth order Markov process when it comes to speech signals.
Sure. Thank you.
Yeah. Okay. Okay, so as I said, right, I mean, HMM is sort of obsolete now. It's not the go-to choice. So then came the revolution of neural networks, right? This was early 90s and so on. This AR models, right, autoregressive models, they date back to like early 19th, 20th century. And then 1980s and 90s, people started looking at hidden Markovian models and other statistical models, similar statistical models. And when neural networks started taking off, right? So came the recurrent neural networks. So known as RNNs. I think if there is one more tutorial, right, you can ask Chandan to talk more about RNNs and BPTT. I will just give you an overview. So the idea in recurrent neural networks is that what you have is that you build a. Okay, so let me before that see what happens in a sequence kind of data is every data point will have a different length, right? Because imagine that we are looking at sentences. If we are looking at natural language sentences, then each of the sentence will have a different length, obviously. So now, if you take a fully connected neural network or an MLP, it is difficult to handle data with different lengths. So now, how do you handle this is the question. So now the one answer is to use what is called as recurrent neural networks. The idea is the following, that to handle this non-equal input lengths. So what you do is share the parameters across time. Okay, what is meant by this? But this is the architecture of a bare-bone recurrent neural network. Say that you have x t here, that is the tth length, and you have the corresponding yt because it's a sequence in sequence out model. Now you have the t minus first hidden state. You have the tth hidden state going out. Okay, this is one RNN block or RNN cell. Okay, now you have parameters that are let's say u, v, and w. Okay, now the relationship between the parameters are given by this, that you have yt is equal to sigma of w times ht minus 1 plus this xt is coming, no? Into u times of v times xt. And the next state, next hidden state is given by right? What I'm writing? No, v times that. What is this? Yeah.
U times xt, right?
Yeah, yeah.
Times 60 into
U times xt plus w times xt minus 1. Yeah. Yeah. So this is one RNN cell. So now what do you do is that you get, have you seen an RNN picture, right? Where people write this kind of a thing? Okay. So, and then they write something called unrolling of RNN. So what that means is that you repeat this. So now if you have a sequence of, let's say, length t, h0, there is x1 here, x2 here, x3 here, and you have h1, h2, and ht, and y1 to yt. Observe that everywhere, so you have the same u, w, and v, exact same parameters everywhere. So this is what is called as parameter sharing across time.
Sir, in the equation for yt,
Ah.
Shouldn't xt be multiplied with u?
xt be multiplied with u. See, the way I have written it is that you take xt here, multiply it with v, and then get yt. And you take xt, but I can write u here perhaps. This is better, no? I write it this way. Yeah, I think this is better. That's what I meant. So here there is w, here there is v, and here there is u. Is it all right now?
Okay.
See, what is important is that you see that the parameters are shared across time, in the sense that for all times, okay, x1 to xt, the UVW matrices do not change. Okay, they are actually shared across time, and that is how an RNN is trained. Okay, now how do we get these UVW matrices? There's an algorithm called backpropagation. Backpropagation through time. Okay, it's not at all difficult. I'll tell you what it is. So we know backpropagation, right? It's abbreviated as BPTT. We know backpropagation, but here what happens is the loss is calculated between YT and XT here, right? You calculate loss between XT and YT, or rather at all points, and you have a loss here at X5 and Y5 and so on. So what you should do is all these losses, right, have to be backpropagated this way, and they should also be backpropagated this way, isn't it? So there are two directions in which it backpropagates, and that is why this algorithm is called backpropagation through time, because there is a backpropagation through time also, time direction also. So you have to basically add those two losses, one across the space, one across the time. That's how an RNN is trained. As I said, no, if you are interested in nice articles, or you can also ask TAs to run through backpropagation through time. But now with like all the things that you have learned in this course, if you just look at the standard descriptions on PPT, you will understand what it is. Okay. So this was being used. Then what happened is there was this. This is okay if you want to solve a supervised learning problem where you have input and output lengths, okay, equal. I mean, you can have different input lengths, different sequence lengths at the input, but the output lengths have to be different. So, but a problem like machine translation, where both the input and output lengths are different. You can't use one standalone RNN. Okay, what is done is the following. So you have an RNN, and by the way, what I just showed you is a naive RNN. Okay, and there are improvisations over it by using things like LSTMs, long short-term memory networks, which are different ways of writing these two equations. Okay, so to avoid this problem called vanishing gradient. So what happens is when you do backpropagation through time, because there is parameter sharing across time, you will multiply the same WUV matrices multiple times with each other. And if the length of the sequence is too large, then the eigenvalues of that will reduce over time, and the gradients will have very less values. That is in a nutshell what is called as the vanishing gradient problem. And you modify these equations so that there is a skip connection sort of thing that is used in resonance, so that the gradients will not vanish. And also what is done is there is no, like, this is only one layer RNN that I showed you. What can be done is you can have multiple hidden states like this, okay, and you have multiple matrices across the space also. Okay, those are all improvisation that I don't talk about here. What is done in cases where the input and output, both of them have different lengths, is the following: that you use a typical encoder decoder sort of model where you have x0 to xt, okay, and we have ht here. You take another RNN or a sequence where you take ht and output y1, okay, and you take y1 and give it as an input to the next unit, and get your y2, and take y2 and give it as an input to this and get y3, and keep doing this till you get the last symbol emitted, which is ym. So typically how it is done in, okay, let's not call it ym, so that is xt, and this is ys. Okay, typically how it is done is that there is a special symbol called end of sequence symbol, okay, which is one of the tokens that is used. Now you keep emitting or you keep generating till you get the end of sequence symbol, and once you see the end of sequence symbol, just stop it there. Okay, that is how uh, uh, the translation or decoding is done. So this is the decoding network.
Sir, you are not audible, at least to me.
Is that so? Hello?
No, sir,
No,
you're
sir,
audible.
you're audible for us, for me.
Okay. So this is the input language, sentence in input language, and this is the translated output. Yeah. So this is the typical encoding decoding model using RNN kind of architectures, and this was actually the state of the art till let's say 20 2014 2015 times. Okay, with some form or the other of it, which is an improvisation over this is what was being done. Any questions so far?
Yes, sir, just one query.
Yeah.
You said we don't send the speech initially, we send the symbols, right? And then
No, this is text translation. No, this is a machine translation task
no,
here.
no, but before this,
Okay.
you said symbols are transmitted, not speech, and speech is regenerated, right?
That you mean for the telephony, right? Long distance telephony and all that. Yes, that is true.
Then how voice can be transmitted actually, or how it will recognize, like if I speak, how the generated signal will match my voice?
Okay. Yeah, that's a good question. See, what is done is uh, the LPC model, right? One, there is content. There is another thing which is your signature, which is that no matter what you speak, there is a particular source signal that mimics your voice. That is your signature. Okay, even that is transmitted, and that does not require a lot more bits. I mean, that will go to speech processing theory. So two things are transmitted. One, the content part of it. The other is your voice signature. Think of it like that. So it's like given your voice, I can overlay any of the symbol, any of the phoneme that I want on your particular voice. That's the idea.
Okay. And for this text thing, the words can be in different sequence when transmitted into translated into different language.
No. Words, no, words will be of different length, I said.
No, length is fine, but one language may have a different order of words. If their literal meaning is taken, then it will not make sense. Like in different language, it will be a different sequence of words.
Yeah, words themselves will be very different, right?
Yeah, and their sequence will also be different, right?
See, when words themselves change, how would the sequence matter? Of course, sequence will be different. So,
How that is learned while predicting?
yeah, see, that is why what you predict is given the previous word that you have I mean, you have given as output, the next word is predicted. That is conditioned on the previous word. No, so you can see here that the output, right, y2 depends on the previous word y1. So if you have enough data, the hope is that the model would see all those combinations implicitly.
Okay, but
So
first will be a direct.
condition done. Condition. See, now the question is, I mean, how would the first word be predicted, right? The first word would be predicted based on the input sequence. And what the input sequence information goes to the output RNN through this last hidden state HT. So it's like you encode the input sequence in this hidden state HT, and that goes as an input to the decoder. Okay, and decoder gives you the first word, and based on the first word and the hidden representation, there is also one other hidden representation here, no, for the decoder also. Based on that, the next words are predicted one by one.
Okay, and is it trained on some kind of literature or
Pairs. They are trained on pairs of sentences from languages. So you have to have a lot of pairs of English and Hindi sentences. and given a pair of English and Hindi sentence, it will be trained that way. It's always
Sorry,
trained on pairs.
pairs you are saying.
Pairs, P-A-I-R-S. Let me write that down.
Okay.
Does it make sense?
Yeah. So even if it's trained on pairs of sentences, it will not kind of do VLOOKUP, right? It will just try to generate each word separately.
Correct. One word after the other, give conditioned on the previous word.
Okay. Thanks.
Okay. Yeah. Thanks. Vivek.
So after the encoding process is over, we just have a single vector, right?
Exactly. That's an issue.
Yeah. So that's exactly I want to know. It's hard to believe that one small vector can
Yeah, it's a you
encode.
point exactly. That was actually an issue, and that is when I'll just hold on to that question. That would be my
Okay.
next narrative.
Okay. Okay. Thanks.
I'm actually building up to transformers, so that I'll tell you why that is an issue and how people solved it. Okay, Santosh.
Yes, sir. So the number of RNN cells will be equivalent to the input sequence in the first layer.
Correct. 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 See, that is because the parameters are shared across time. We are just repeating the same RNN cell one after the other with a different input and the hidden layer. That's all. But the weights remain the same across time.
Okay. Also, my second question is that right now we have only two layers. If we have multiple RNN layers, so the final hidden state of first layer will be passed to the second layer, and then like that. So the output will be passed to next layer.
There will be
That's
two things, right? If you have like a two-layer thing, there will be one that goes like this, one that goes like this.
uh-huh.
Yeah, you can have any number of RNN layers, one after the other. Well, any number of hidden
Okay.
layers, one after the other. You can make it deep.
Okay. Okay. Yeah.
Yeah. As I said in the beginning of the course, right? Like this is not a course where I teach NLP fundamentals and architectures, right? So, I mean, one can actually teach a full course on sequence modeling and how RNNs work and a lot of nuances there. But as I said, this course is more on you now you know what this course are. We are almost coming at the end of it. But yeah, so an overview of RNNs are like this. Any other question on this? If not, let's move. So this was, as I said, no, this was the state of the art till for machine translation. Okay, like till let's say like 2010s. Okay, 2010s. This is what was being done, and since this is not as you can imagine, right? As Vivek was saying, there's only one hidden state that has to compress all the information regarding the input sentence. It was not doing great, and that's why machine translation was not available commercially at large scale beyond academic labs, right? So then came this nice idea, which I'll tell you. This x1, this is xt, and you have y1, y2, uh, up to y, what did we call s? Okay. Somebody thought that, okay, why only have one hidden representation compress all the information that is regarding that I mean regarding the entire input sentence. So can we do something else? So this is like that hierarchical VAE idea. So somebody said, okay, we'll do this. That we will take this is the first hidden representation. This is the second hidden representation hidden representation corresponding to X-ray and all that. So what is done is that you take all of these, okay? Take a linear combination of all of these. So let me write it neatly. Compute AJ HJ, okay? Take H1, H2, H3 and HT and compute this and give this, let's call this AJ cap, okay? AT cap, okay? And give this as an input to this thing, okay? And have as many AT. So there is A1, okay, and there is A2. You have another this thing which is, let's call this as A1. This is AJ2HJ. You have A3 cap and so on, okay? And give all of these as inputs to the corresponding output sequences. Does it make sense? So what we are actually saying is take a linear combination, okay, and here the A's are also learned, okay. Do you understand what is happening? So now instead of making one hidden layer have all the information and compress and then decode, saying I will tap the hidden representations from each of the time steps from the encoder side, have a learnable linear combination of that, and then give it as an input while decoding. Do you understand this?
Sir, what is A here?
A is a learnable constant.
Sir, how is AJ1 different from AJ2?
They are learned differently, no?
But
So
they are tapped from the same nodes,
correct,
right?
but these indices are taken to be different. So here what you do is, here you only take J from like 1 to 2 and you make 1 to 3 and you take like just cumulatively do that. Is that okay? Again, there are different improvisations over it, but the idea is clear, right? What you do is you take a linear combination of hidden layer representations and learn the weights with which they have to be linearly combined, and then give it as an input while you are decoding it. Is this idea clear?
So, sir, here number of linear combinations equal to number of Ys, right? I mean sequence.
Number of Ys, correct. Okay. Now, do you know what this thing is? This is actually what is called as attention. This is what is called as attention. Okay. Like say like RNNs with attentions. This is RNN with attention. Okay. What you are doing is that you take the linear combination of hidden layers and then give that as an input to the while decoding. So this received a lot of attention. Okay. And this gave a significant boost in terms of what what we could achieve using machine translation. Okay. So then came this thing, no, which is the transformer architecture, where they said, okay, see, anyway you're using attentions here, okay, why even have an RNN cell? Because you end up with the problems of vanishing gradient and all that if you have very long sequence lengths. So why not create an architecture, right? So come this transformer, which is an attention only architecture without a recurrent nature structure. Without recurrence. Yeah, that is what a transformer is all about. Okay, it is an attention only architecture without recurrence. Um, I'll briefly talk about what uh, attention is. I mean, this transformer is. Okay. Now you have like input sequence X that is equal to X1, X2 up to Xt, right? Okay. Now a transformer is some function f theta that will take each xj and gives you a corresponding zj. Okay. So now what does it do is, given a sequence X, data X, okay, a transformer outputs a sequence of representations or hidden layers or hidden representations. I mean, you don't have to call them hidden representations Z, okay, for corresponding to each of the input tokens. So for every input token Xi, there is a corresponding representation Z, okay, that is how you do it. So now the question is, how do you get the ZG, right? Now Zj is given as a linear combination of alpha j of what is called as the the value vectors. Okay. Now I'll tell you what these value vectors are. So now, given a data token xj, okay, multiply that with 3 matrices. Call one as the query matrix. So this is transpose xj, okay. Then you have the value matrix and the key matrix. Okay, what are we doing? We are getting 3 particular vectors. Okay, so here all uh, obtain 3 vectors. Okay, as this here the WQ, WV and W and WK are learnable and learned through back propagation. These are the learnable matrices. Do you understand? So what is happening? Given a particular data point, you take each of the token corresponding to it, which is a vector. Okay, pre-multiply that with 3 matrices. Okay, and you get 3 other vectors. Call them query, value, and key. Is that okay? This is called the query vector. Any questions so far?
So xj should be the entire sequence, right? Not one of the
No.
components.
It's one of the components. It's not the sequence. Because for every vector in the sequence, okay, you compute the query value and key.
Sir, X in itself is a vector, right?
X is a sequence. X is a sequence that has t number of vectors. Is that okay? See, how did we define a sequence? We have defined a sequence this way, right? A sequence, every vector, right? A sequence is a t length uh, tuple where each component of it is a d-dimensional vector. So every xj is a vector here. Okay? You get these three vectors, right? So now then what you do is you define the representation corresponding to the jth token as a linear combination of all the value vectors corresponding to all the other tokens in the sequence. Okay. But the question is, how do you get this alpha j? How is this alpha j cotton? So what you do is that you multiply the jth query, take the inner product of the jth query, which actually I should call it alpha. Okay, hold on. So I need one more symbol here. This is for j. So now for okay, let me just write it. So now you take the jth query and multiply that with the uh, ith key. Multiply that with the ith key. Okay. Then what you get is you get the attention score or the weight score corresponding to the jth query and the kth key. Okay. So this will give you alpha j I, which is a scalar. Fine. Now you need to multiply this. Cumbersome. That's why I'm thinking, how can I simplify this? Just give me a second. Let me think. Yeah, that is one value. And I need to look at this is to fix this j and this is what it is. Do you understand what's happening? Okay, so I'll tell you. See, now what is happening is that we are given, I will write it here, it will be easier. I thought this class would end early. So these are sequences, right? FT sequences. What is first done is that you multiply these with the W matrices and get the corresponding queries. So this is Q1, Q2 up to Qt. We have these queries and we have these, multiply that with the K matrix and get the keys. Okay, and then you have the multiply that with the value matrices to get the values pt. Okay, now what we are doing is we have to get zj. Okay, z1. To get z1, what you do is you take the inner product, okay, between the query corresponding to the first token, okay, with the query keys corresponding to all of the tokens. So this is you take an inner product like this between these two. These two, these two, these two, and these. This will give you, what will this give you? This will give you, the way I have written it, this will give you alpha 1 1, alpha 1 2, alpha 1 t. Is this okay? Are you getting it? Any questions on how are we getting alphas? This is important, so please tell me if you don't understand this. Hello? Hello, am I there? Am I audible?
Yes, sir, you're audible. Yes.
Okay. Yeah, total radio silence. So I don't know how to interpret it. Is it okay? Did all of you get how to get these alphas? Yes or no?
Yes, sir.
Okay. Now, how are these V's obtained? Sorry, Z's obtained? They are obtained by taking a linear combination of all these values, okay? And they are weighted by the corresponding alphas. Okay. In fact, it's actually a convex combination. So what is done is you don't use alphas, but you use betas. Okay, they are beta ji's. Okay, where betas are you take alphas. Okay, and divide that by some constant d, which is the dimensionality of data, and then you do a, just say that alphas are softmax over alpha divided by t. That's all. So now why do you do this? This you do because all beta j's, right? They are bounded between 0 and 1 and they simply sum to 1. That is why you do this softmax, so that the linear combination of the values that you are taking, okay, is bounded between 0 and 1. So now let me repeat what is done here is that you given a token, given a sequence of tokens, okay, which is an input data point, one input data point, you define three matrices, call them as and multiply those data points with these three matrices, okay. They and call them as the query, value, and key vectors. So corresponding to each of the token, you will get three vectors, okay. Then the representation corresponding to each of the input token is a linear combination of all the value vectors corresponding to each of the tokens. Okay, that's all. Now, how do you define which of the, I mean, how do you get what is the weight factor for the linear combination? To get the weight factor for the linear combination, you use the query and key vectors. How? You take the query vector corresponding to the token of interest. You take an inner product of that query with all the key vectors corresponding to all the tokens and normalize it so that it lies between 0 and 1. That would give you what is the weight or scale with which you have to scale each of the value vectors to obtain the representation corresponding to the token of interest. Okay. So this is one transformer block. With a single head, they call it. And there is also a counterpart called the multi-head attention. I'll talk about that in a while. But yeah, any questions so far?
So if we shuffle the x1 to xt, then the z's will also be shuffled. In the sense, like if the sequence changes.
Yes, that is true.
Okay, so please go ahead. Yeah. So does it, when it changes, does it still remain do the individual values still remain the same, or will they also change?
No, they do change. They do change depending upon what the sequence, what the what the relative positions of each of the tokens are in the sequence. They do change.
Okay. Okay, sir. Yeah.
Okay.
Sir, is the T fixed here?
Yeah, T is
Like,
fixed. Yeah. So you keep hearing about this context lens of all these LLMs, right? They say that they are coming up with larger and larger context length. This T is what is called as context length. Now it is like 2500 is what the context length of GPT is and so on. That is the context length. So now you might ask this question. We started by saying that each of the input data point will have different sequence length. How does transformer handle it? They handle it by just zero padding. That's all. So they keep a fixed context length, and then if that length is equal to the highest possible length of the highest possible sequence, and for all the other sequences that have length less than the highest possible length sequence, let us zero pad them and make them equal length. And now, how does that? How is that handled? The hope is that that is handled by the appropriate representation. Okay, the attention for, or rather these alphas and betas for that corresponding uh, zero tokens will be zero, and it has been observed that they will actually ignore them.
okay, sir. Thank you.
Okay.
Yeah, one more point here. So, I mean, here that position information is not present anywhere, right?
Yeah,
So,
yeah.
if you shuffle the
Yeah.
sequence.
Yeah. Hold on. That's correct. That is correct. And do you recall that during our DDPM discussions, I talked about positional embeddings, where we have to give T the time information also as an input, right? In transformer also, what is given is, in addition to this, T is also given as an input using the positional encoding for the precise reason that you said. Positional embeddings, and we talked about positional embeddings during the LLM lectures. Sorry, the diffusion lectures. Okay, fine. Now, how do we finally solve the sequence to sequence problem? Is that we have here a transformer block. There is one other like normalization layer that they use, and also a skip connection like ResNet and so on. Right, I'm skipping that. The major focus is on attention. Okay, so the enormous amount of literature on this, you will understand. The difficult part is how the attentions are actually uh, computed. So you get Z1 through ZT. Okay, and there is this. This is the encoder. And similarly, there is a decoder block. Okay. What does it do is it will take these uh, embeddings or the representations given by the encoder as the input, okay, and then do an autoregressive generation. So now you get one y1 and you take y1 as an input and give it just like you do it in RNN, right? So you take that and you get y2 and you take that as give it as an input and so on. Okay. In fact, this is exactly what a large language model does. I mean, okay. So this is BART kind of large language model. This is how the training happens. In addition to this, there's also uh, uh, like attention blocks between the encoder and decoder. Okay. These are called cross attention or details. So this is whatever we saw, right, which is attention between the input tokens, that is called self attention, and there is also attention between the queries keys of the encoder and the query keys of the decoder. That is called cross attention, and this is actually the bare bone of what the modern day LLMs do. Okay, so now you know that, right? I mean, you are given a particular prompt. When you give a GPT a prompt, what you are actually doing is giving a prompt to the encoder, and depending upon your prompt, this decoder generates. And how is the training done? Surprisingly enough, training is completely supervised. Supervised training using KL minimization. I mean, like the usual cross entropy loss is what is used. That's all. The bare bone training of an LLM happens in a completely supervised way. Okay, using KL minimization. So you have pairs of these tokens, input and output tokens. In fact, uh, actually, what happens is that you first train an embedding extractor using the self-supervised learning techniques that we just saw, no, masked reconstruction. Last class we looked at masked reconstruction. So what is done is, okay, let me just talk about it perhaps. So first thing that is done is, okay, this the broad level LLM training typically happens this way. So there is first a self-supervised pre-training. Where, and by the way, architecture wise, right, everything that is used in an LLM today are transformers. You take a transformer, okay, take an input sequence, and you get the embeddings, and the task is to simply reconstruct the data back using the encoding. So technically speaking, there is also an encoder decoder model here, another transformer. This is the decoder C1 to C3, and what is given as an input is a version of X, okay, where it is where X cap is a masked version of X. This usual self-supervised learning task that we do, right? And these Z's will go as input to the decoder, and what is given back is the true data. So this is exactly what is done in BERT, okay? So you have an encoder and a decoder, and encoder takes a masked version of X with random mask, and it reconstructs the data. So this is what is called as the self-supervised pre-training. Okay, this is done. Once this is done, you get embeddings of data. So then you use a usual encoder decoder model in the second stage using supervised fine tuning. Supervised fine tuning, okay, on the embeddings obtained in the obtained using self-supervised learning. See, surprisingly, the inner workings of LLM is very, very simple. I mean, from an ML complexity perspective, all you do is take a lot of data and do a self-supervised pre-training using mask reconstruction kind of tasks. And then they do a supervised fine-tuning on whatever data that you want to fine-tune it on. That's all it is, using transformer as the backbone. Now, I mean, there are nuances here where when you are doing fine tuning, right, you may not have a lot of data. How do you do it without fine tuning? There is this retrieval augmented generation or RAG kind of frameworks, and also this low rank reconstruction, low rank approximation for fine tuning, where the problem is that if this pre-training, the model is like billions of parameters, you can't fine tune on all billions of parameters. You just take a subset of them and then fine tune. And all those are other improvisations and nuances. But at a broad level, this is exactly what happens. So there's a transformer which is the big bare backbone architecture. You take data, typically from the entire internet, and do a self-supervised pre-training using uh, mask reconstruction task, which we have seen. And then whatever, take that model which generates embedding and do a supervised fine tuning on whatever data that you want. And if you do that, then you already have a like GPT-2 or GPT-3 that is there. Okay, that's what it is. Any questions on this? Yeah, as I said, no, this is not a full course on LLM, so I don't go to the nuances of it. Just wanted to introduce and put it in the perspective of what the so-called modern LLMs are doing. So this is exactly what it is. As I said, no, in terms of ML complexity, it's very, very simple. There is a self-supervised pre-training using transformers, and there is a supervised fine-tuning that is happening using usual cross-entropy kind of losses. Right? And the underlying architecture that is used is a transformer. Please also remember the word generative AI, right? It is used in a very, very loose sense today in outside of expert community, where it is used for like image generation, language generation, and all that. Whenever there is a sequence task that is done, no, a transformer is used, and this kind of recipe is followed. Wherever there is an image generation task, no, typically transformer is not used, a diffusion model is used. Right? Okay, so that's about it. That's all I wanted to cover in this course. Yeah, so let's maybe just stop recording.
Yeah, what is drag? You talked about little, right? What is that? We heard it many places, right in the Generative area.
Yeah. See, the thing is, even when you fine tune, right? Sometimes it may not suit your purpose. It's think of it like using an additional data that you have, okay, without doing a fine tuning. I mean, supervised fine tuning on it. You use that additional data to guide your transformer or generator in some way. Or the decoder. See, in all our generative modeling, right, we know